This is Mr. Martin. These are notes for Unit 3, conic sections. We're talking about hyperbolas. This is for pre-calculus advanced. So this is going to be our last conic section. We've talked about circles, parabolas, ellipses, and now we're talking about hyperbolas, which is a different slice of our cone. So let's start with the definition. The definition of a hyperbola, just like the others, is based on a set of all points. So for this one, we have the set of all points such that the difference between 2 points, and these 2 points are called foci, is constant. So this is a little bit similar to what we talked about with ellipses. With ellipses, we were talking about the sum of 2 segments being constant. Here we're talking about the difference of 2 segments being constant. So I'm going to label this segment here D1 and this segment D2. And then I'll label this one D3 and this one D4. And what I'm going to do is I'm going to look at the difference between D2 and D1. So I'm going to subtract the length of those segments. So I have this point out here, and I measure the distance to this focus, and I measure the distance to this focus, labeled F sub 1, and I'm going to subtract those distances. Then I'm going to do the same thing with D4 and D3. So I've got D4 minus D3. So if these points are on our ellipse, then all of these differences, these 2 in particular that we're talking about, would be constant. Okay, so then we could do the same thing with these 2 over here. If I subtract these 2 segments, they would also equal the same as whatever I got from D2 minus D1 or D4 minus D3. Okay, so that's the basic idea of our hyperbola and how it's generated. So it's a little bit interesting that when you have these 2 foci, you can get a parabola-like shape on this side. Notice we have these asymptotes now that we're going to be approaching. We'll talk about those. Or we can have a similar parabola-like shape that goes in the opposite direction. So with parabolas and circles and ellipses, you end up with just a single shape, but with a hyperbola, there's a set of points on either side of your center that the difference between the 2 points is constant. So keep that in mind. Let's point out some of the other stuff in here. We've got our center right here in the middle again. In this particular example, it's at the origin, but it won't always be. Our center again is going to be HK, just like it was for ellipses and circles. And then notice again we have this distance A from the center. So from the center to the vertex, this is a vertex over here. And then from the center to the vertex over here, that's the value A as well. And then again, notice the value C here, that's from the center to a focus on the right, and from the center and a focus on the left. And then again, if we turn it, then our A's and C's would be going vertically. So we've got 2 different standard forms here, one for horizontal and one for vertical. And I want to point out with ellipses, basically we were looking for the larger denominator, and that told us whether the ellipse opened up vertically or horizontally. If you notice, for these, the a squared and b squared are the same. So for horizontal and vertical, the a squared and b squared, they don't change. But notice that our numerators change. So for a horizontal transverse axis, I have x minus h squared first. And for a vertical transverse axis, I have y minus k squared first. And then our other key difference, remember our definition talks about the difference of two distances. We've got this minus here. All right, and this is going to add a whole another level of issues when we start finding our standard form from our general form, because we're going to be factoring negatives, and you need to remember that. But we'll talk about that more when we go into some examples. Okay, so here's our two vertical and horizontal pictures that go with these. So again, HK over here, this is our center. So there's our center for both of these. And then I've got the distance from the center to the vertices. So I have a vertex here and a vertex here. So vertex, I've got one over there and one over there. And then I'm just going to draw in some foci, just arbitrarily there, but just so we have an idea, foci. So there's our foci. And then we have this other distance b. We've got this rectangle here. Sometimes it's called a central rectangle. So, and we're going to be drawing those rectangles whenever we graph our hyperbola. So notice that one of the dimensions is 2a. So we start at the center and we go a one way and a the other way. And then the other dimension would be 2b. It's kind of like our major and minor axis for ellipses, except we're going to call them a transverse axis. So that's like our major axis, and then we have a conjugate axis. That's like our minor axis. And again, those are 2a and 2b. So we'll be drawing in that rectangle. So we really don't give these 2 points a name here, but we do use them to draw our central rectangle. Okay, so there's our vertices and foci for our horizontal. And then when we turn it vertical, I've got my vertices here. Vertices. And then again, I could draw in some foci. Foci, I've got one there and one there. And again, our center is right there. So those are the parts. Again, they're very similar to what we had for ellipses, except if you notice, our foci are farther away than our value of a. Okay, so now C is going to be bigger than a. With an ellipse, C was always inside the ellipse, so we knew that C had to be less than a. But for a hyperbola, now the relationship between these is that c squared is equal to a squared plus b squared. So here's our relationship between a, b, and c. All right, and then finally, if you notice, we've got these asymptotes here that go through the vertices of our central rectangle. Okay, and we're going to use these to help us sketch in the hyperbola. We've got the equations of these. So notice that these two equations, if I move the k back to the left, it would be y minus k. All right, just like our standard form up here has y minus k, and then I still have an x minus h. Okay, so all we do is we move the k over to the other side so it becomes positive. So instead of y minus k, I have y equals positive k. And then I have this plus or minus because the asymptote that goes up to the right has a positive slope, and the asymptote that goes up and to the left has a negative slope. And then we have our x minus h. So if you have your standard form already, really it's just a matter of finding the slope, whether it's going to be b over a or a over b, to fill out your asymptotes. So personally, I never remember which is b over a and which is a over b. I always use my graph. So if I look at my central rectangle here, if I want to look at the slope of this line, we always do rise over run. So I'm going to go up b, that would be my rise, and I'm going to go over a, that would be my run. So my rise over 1 would be b over a, which is my slope here, b over a. If I look at my vertical, again I start at the center. I'm going to go up a value of a, and then over a value of b. That would be my rise over run for this positive slope here. That's how I know that my slope is a over b. Alright, so with a little bit of practice and your previous knowledge from ellipses and circles, you should be fine with these. If you have any questions, make sure that you ask me. And you can move on to the next video where I'm going to take you through the first we do example. So we'll see you in the next video.